Welcome back. We've been proving a few things with sets, and now we're just going to prove a few more. So we're going to do some proofs involving Cartesian products and power sets. And these are a little bit more complicated. There's a few more idiosyncrasies, so we'll put them in a separate video. They just need a little bit more practice. So Cartesian product and power set proofs. So here's a Cartesian product example. We've got A, B, and C be sets, and then this product of A times B union C is A times B union A times C. So it's a distributive sort of result. So we do a bit of scratch work. So first of all, I'm going to prove one inclusion and then the other. So we'll prove that this right-hand side is a subset of the left-hand side. So that's what I've stated here. So since it's a Cartesian product, I already know that the elements on each side are actually ordered pairs. So now rather than pulling out an element, say A, I'm going to pull out a Cartesian pair because it's going to make it easier for me to understand where the first element comes from and where the second element comes from. So I'm going to pull x, y out of the right-hand side. Now, this is going to split into two cases because it's a union of two things. We know that x, y is in A times B, namely the first part of this union, or it's in A times C, the second part of the union. That naturally gives us two cases. So case one, if x, y is in A times B, we know by the definition of the Cartesian product, that means that first thing comes from A and the second thing comes from B. Now, there's a nice little bit of logic we can use here that if y is in the set B, then it's in the set B union anything else. So we can pick B union something useful. Now, in our result here, we need B union C. So since y is in B, we know it's in B union C, which is just what we need because it's in x is in A, y is in B union C. That's exactly what we need for the left-hand side. Now, case 2 is very, very similar. X, y is in AC, so x is in A, y is in C, and again, we can use that same bit of logic, y is in C, union anything we want, so we might as well pick something useful. Let's pick C union B. So in both cases, we have that x is in A and y is in B union C. So x, y is in the left-hand side, which is just what we need. Okay, so if x, y is in the right-hand side, then it's in the left-hand side. So we've proved that inclusion. Now the other inclusion is going to be quite similar. So continuing our scratch work along, we do that the left-hand side is a subset of the right-hand side. So again, we pull an ordered pair out of the left-hand side. So let's do so. Then we know that x is going to be in A, and then y is in B union C. So that means y is in B or y is in C. So again, two cases. When y is in B, we know that x, y is in A, B. And again, we can use that logic we just used previously, that if something is in a set, then it's in that set union whatever other sets we want. So if x, y is in A times B, then it's in A times B union whatever else we want. And in this case, it makes sense to union that set there. Similarly, when y is in C, then we know x is in A, y is in C, so x, y is in AC. And then x, y is in AC union whatever else we want. So again, we pick the useful set here. So in both cases, x, y is in the right-hand side, which is just what we need, because we've shown that if x, y is in the left-hand side, then it's in the right-hand side. And so we've proved both inclusions, so we've shown that these sets are indeed equal. So we just have to write it up nicely. Okay. So, well, hold on. Write it up nicely. Well, you can write that up nicely. You know how to do that sort of thing now. So I'm just going to show you the scratch work for that problem, and maybe we'll do the full proofs for a couple of other things. So let's go into a power set problem, and in particular, let's do a little bit of warm up here. So we need some results that are going to make proving these power set results a little bit easier. So here's the first one. If x is a subset of A, then x is a subset of A union whatever other set we like. So this is just continuing the logic that we had, that if x is in a set, then it's in a set union whatever else we want. So we're just extending those results that are element-wise into results about subsets. So if x is a subset of A, it's a subset of A union B. And we can prove this quite directly, namely, if we let x be a subset of A, so that's the left-hand side, then if we assume and pull out an element from x, we just have to show it's in there. So if we pull an element of x, well, it's in A, just because x is a subset of A. Well, then it's in A union whatever we want, and so we pick B. Okay. So we've shown that x is a subset of A union B. Similarly, for this second result here, if x is a subset of the intersection of A and B, then it must be a subset of A. And this again follows very, very similarly. So we assume that subset result, the left-hand side, the hypothesis is true, so X is a subset of A intersection B, and then we're trying to show this inclusion here. So we pull an element out of this set on the left, so we pull some X out of there. Well, because X is a subset of A intersection B, then we know little x is in there, which means X has to be in A, which gives us this result here. Then finally, we have an if and only if here. If X is a subset of A and a subset of B, then X is a subset of A intersection B, and vice versa. Okay, so we can prove each implication in turn. So here's the first implication. Let's assume X is a subset of A and X is a subset of B, and then pull out an element of X. Well, because X is a subset of A and B, then we know that element of X is also in A, and it's also in B, so it's in the intersection. So that gives us that implication. Now we can do the reverse implication. So again, we assume this to be true. So X is a subset of A intersection B. Well, since A intersection B is a subset of A, we've proved that that means X is a subset of A. Because if X is a subset of this, and this is a subset of A, then X is a subset of A. And very similar reasoning gives X is a subset of B. And so that's proved the reverse implication as we need. Okay, and so we'll use those in a moment when we prove some power set results. So here's a simple power set example that describing how power set operation, the operation of forming the power set, how that interacts with the union operation. So if we let A and B be sets, then the union of the power sets is a subset of the power set of the union. And the reverse inclusion definitely does not hold. So this is definitely a subset, but the reverse inclusion, if we try to go the other way around to show that this left-hand side and right-hand side are actually equal, that doesn't hold. And we'll prove that in a moment. So let's do the first thing first. Let's start with this inclusion and show that it's true, and then we'll find out why the reverse inclusion does not hold. So notice this is equivalent to saying that if X is in the left-hand side, then it's in the right-hand side. So now I've taken a capital X here because the things in the left-hand side are sets. They're subsets of A and B. So I'm going to pull out a set from the right-hand side because it's an element of those power sets, and then you show that that set is actually in the power set of the union on the other side. So let's pull out X from the union of those power sets. Well, this means that X is either an element of the power set of A or it's an element of the power set of B. In the first case, if X is in the power set of A, that means X is a subset of A, which is what the power set does for us. And if X is in the power set of B, then X is a subset of B. Now, if X is a subset of A, then, by reasoning that we did a couple of slides ago, that means X is a subset of A union B. And so X is in A union, or the power set of A union B. And the other case, namely if X is a subset of B, is very similar. Okay? So we can make all of that work and we can write it up nicely. Let's look at the reverse inclusion now. So the reverse inclusion, well, notice that this is a statement that we're making here, where the power set of the union is a subset of this. This is really a for all sets A and B. It's really a universal quantified statement. And so when we try to show that it's false, a disproof can just be a counterexample, because all we need to do to show it's false is there exists sets A and B so that this is not the case. So notice the right-hand side here. If we pull something out of the right-hand side, it's either an element of the power set of A or it's an element of the power set of B, which means it's a subset of A or a subset of B. On the other hand, when we pull something out of this side, it's a subset of A union B. So while the right-hand side here is either, so hold on, that should be a L for left-hand side. So when we pull something out of the right-hand side, it's either in the power set of A or in the power set of B. But if we pull something out of the left-hand side, that set that we pull out of there could contain elements from both A and B, which cannot be the case of the thing on the right-hand side. So we can try to construct a very small counterexample to make this work. And indeed, that's what we should do when we try to make counterexamples, is we might get one that works, and then we should look to see if we can make it even simpler. Okay, so we can construct a very small counterexample here. So in particular, if we let A be 1, the set that contains 1, and B be the set that contains 2, then the set 1, 2 well, that's A union B, that's in the left-hand side, but it's not in the right-hand side, okay? Because the right-hand side will just be the empty set, and it will be the set that contains 1, and it'll be the set that contains 2. It won't include this set with an element from A and an element from B, okay? So that shows that the left-hand side is not a subset of the right-hand side, and that's enough to disprove that reverse inclusion. So we can write this up. So proof, we tell the reader the structure we're going to use, we're going to prove that first inclusion and then show that the reverse inclusion doesn't hold. So the first inclusion, let X be in the left-hand side, then X is a subset of A or it's a subset of B. If it's a subset of A, then as we showed a few slides back, that means X is a subset of A union B. And similarly, if X is a subset of B, it's a subset of B union A. And in both cases, this implies that X is in that power set. So if it's in the left-hand side, then it's in the right-hand side. To disprove the reverse inclusion, we use a counterexample. So in particular, if we set A as the set that contains 1, B is the set that contains 2, and X is the set that contains 1 and 2, then we see X is in one side, but X isn't in the other side, and that's enough to show that that inclusion doesn't hold. And that's enough to do the proof. Okay, another one. So let's do another power set result, and this shows that the intersection of power sets is the same as the power set of the intersection. So this tells us that the previous result told us that the union and power sets don't play quite so well together, but this one's enough to tell us that the intersection and power sets do play well together. And so again, we have two inclusions to prove here. We have to show left-hand side, subset of the right-hand side, and vice versa. So let's assume that X is in the left-hand side. Then we know that X is in the power set of A and X is in the power set of B. And that's enough to tell us that X is a subset of A and a subset of B. And again, we showed just a few slides back, that means X is a subset of the intersection of A and B, which means it's in the right-hand side. Now, if we let something be in the right-hand side, then we showed previously, well, that means that Y is a subset of the intersection, which means it's a subset of the first set and a subset of the second set, and that's enough to tell us that it's in the left-hand side, which is what we required. So now we just have to write that up nicely, and so we just, again, tell the reader what's going on. Our proof, we prove each inclusion in turn. So we assume that X is in the left-hand side, which tells it's in the power set of A and the power set of B, and so it's a subset of A and a subset of B, and hence, by the stuff we did earlier, it's in that intersection, and so it's in the right-hand side. Similarly, if we pull something out of the right-hand side, we know it's in the power set of A intersection B, and so is a subset of A intersection B, and as we showed earlier, that means it's a subset of A and it's a subset of B. The first tells us it's in the power set of A, second tells us it's in the power set of B, and so it's in the left-hand side as we needed. And we'll stop there.